Hello everyone and welcome back to another pattern recognition lecture video. So in this video here we'll be going over hyperparameter tuning for deep neural networks. So here we have the topic overview of the videos in this series, where in the first video we went over neural networks and deep learning, the basics about them. In this video here we'll be going over how to improve the deep neural networks via hyperparameter tuning, regularization and optimization. And in the following videos, we'll be looking at convolutional neural networks and sequence modeling. But first, let's just have a brief repetition of some of the most important things from the basics about neural networks. So at first, just something about the architecture design of these neural networks. The main one you'll see in this video here, and also the first video that you saw, is these fully connected networks, where if we have a look at an architecture view here, then a single neuron here, for instance, from the first layer will be connected to every single neuron in the following layer. And the same goes for the neuron, all the neurons in the first layer. They will also be connected to every single neuron in the following layer again. And the idea behind having this layered networks is that multi-layer networks are preferable over three-layer networks because they often generalize better. And the thing with these fully connected, because obviously we could remove maybe some of these connections that maybe the weight for these connections are close to zero. But in deep learning frameworks, we're really taking advantage of matrix multiplication, so everything we know from linear algebra, and we can see here that everything it takes to compute the output of the first hidden layer is a simple matrix multiplication and addition. So if we keep everything in fully connected, then we just have a simple matrix multiplication. Then we can compute do all the computations in our network. And as we also saw last time, then there's a simple computation for once we have these fully connected networks, then we can easily compute how many parameters we actually have in our network to fine-tune later on. And as also mentioned, then the bias term is often not shown in these architecture design, but in fact, it has a node which is just set to 1, and then the bias terms here they are described on the node between this one node and all the units in this case here in the first hidden layer. So deep neural network consists of a lot of neurons, and one way to model these neurons is via a simple perceptron. So how is the perceptron structured? It takes some input, maybe just from the very first layer here, x1, x2. Then all our inputs, they are multiplied with some kind of weight. So here we'll have x0 multiplied by 0.7, here x1 multiplied by 0.6, and so on. And then we're summing up all of these inside the neuron. And finally, we have some kind of activation. So in the case of a simple perceptron, we just have the step function. So we see if the value after the sum is above or below 0, and then we set the output to 1 or 0. But we also talked about the disadvantages in the first video, namely that we'll have the derivatives of 0 everywhere except at 0, and at 0 is not defined. We don't have anything defined about the derivative here at 0, where it's like this infinite step in the step function. And usually in a deep neural network, what we are learning from is exactly the gradients. So if we do not have any gradients, we essentially have nothing to learn from. Then I just wanted to include here that I also talked about these deep neural networks. Quite often people are talking about them that they are modeling how the brain works, which I do not see as being completely valid. So it's more they occasionally draw some insight from what we know about the brain. And neural networks are therefore not modeling how the brain works, but as mentioned, just draw some insight from how the brain works. A very popular alternative activation function instead of the step function is the rectified linear unit, so the ReLU activation function. And the way that works is that it just sets everything if x below 0 to 0, and everything above, it just passes x straight through the activation function. And if we look at the derivative, then it's also very simple to compute. So it just sets everything to 0 below, if x is below 0, and everything above, it's 1. But what you also see here is that it's not well defined at 0, which is a problem in theory, but in practice, it turns out that in fact it's not a problem at all. In a deep neural network, we'll need to be able to quantify the output of this network with respect to what the output should have been. And for this, we use a loss function. In this case here, the cross entropy loss, which was also introduced with logistic regression, can be used with models that output some probability value between 0 and 1. So it's very good in cases, for instance, in binary classification tasks, where you can then optimize over one class. So put out 1 if it is the class that you are trying to classify, or 0 if not. And this loss function here is a huge improvement from the quite simple mean squared error, which was heavily used in especially the 80s and 90s. And instead of binary classification, if we have multiple classes, then exactly this loss function here can be extended to the categorical cross entropy for multi-class classification. So that was a very brief summary of just some of the most important things from the introduction video. Now we'll move on to the content of this video actually, which is hyperparameter tuning, regularization, optimization. And we'll first be looking at what is the difference between hyperparameters and parameters in neural network. What dataset are we actually using to optimize these networks? How to tune the hyperparameters of a network, and lastly something about optimization algorithms. What are actually parameters and hyperparameters in a neural network? So let's first start out by looking at parameters, which is all the weights and bias terms in the network, which connects to all the neurons, essentially everything from the input to the output that we are trying to optimize over. And then we have all the hyperparameters, which is what we can use to control to find some optimal values for the weights and the bias terms. So first we have the learning rate, which is this rate controlled in a learning algorithm, for instance in gradient descent. Then we can control how many number of iterations we want to optimize over. There is different kinds of regularization, which we'll be looking at. You can look at network architecture, where you can have number of hidden layers, number of hidden units, the choice of the different activation functions. All of this is essentially different hyperparameters. And also the optimization algorithm that you're using. For instance, we'll later on in this video be looking at momentum. And you can also change the batch size. Instead of optimizing over your full dataset, you can use what is known as mini batches. Looking at the dataset, then we would often split the dataset in 3 different categories. First a training set, then a validation set, and finally a test set. And traditionally, when using a smaller dataset, maybe with between 100 and 10,000 items, then a split would quite often be 60-20-20 or even 70-30 in case you are not having a holdout test set to be tested on afterward. But nowadays, when we have what's known as big data, above 1 million items in our dataset, then around 10,000 examples should be sufficient for the validation and also the test set, which makes the split more like 98% for training and 1% for validation and 1% for testing. And a cycle could look something like this here. So you're in the training cycle here, optimizing over your training set, so the 98% of your data here. And then you have the 1%, so the validation, you're optimizing over here. So it's to ensure that you're not overfitting just to your training set, but it should also generalize well enough to your validation set. And here, between these two, then there is a lot of hyperparameters that we just discussed before that you can then tune. And once you're happy with all your hyperparameters and the performance of your network, then you can finally go ahead and do a testing on your holdout data set, so your testing set here. And important to note here is that once you have tested on your test set, then you should not go back here and do some more optimization, because then you would use your testing set also to optimize over your hyperparameters. So very important is that you should not optimize your hyperparameters on the test set. When training a neural network, then you'll often hear about the bias and variance trade-off. So there is a very extremely simplified, there'll be these three scenarios. So underfitting, so you're having a too high bias in your network. Overfitting, which is the one to the right here, where you are essentially able to classify maybe everything correctly in your training set, but you've often failed to generalize well enough on your test set. And then there is something which we trying to strive for, which is the good compromise, the thing just in between, where we might still have some error on our training set, but it's generalizing much better to the test set. Obviously, in high-dimension cases, such as image classification, it is not really possible to visualize the classification hyperplane as shown here above. But instead, we can look at some classification accuracy. So this here is just some very coarse rules that you can look at, which is if you have high variance, then you would most often see that your validation error is quite high compared to your training error. And if you have high bias, then both your training set and validation set would be quite high. Then you could have high bias and high variance, meaning that you have quite high training error and even higher validation error. And then what we're trying to strive for is this low bias, low variance, where you have a good performance on your training set and a good performance on your validation set. But this here is given that the classification is easily solvable by humans. Like the humans would have around 0% error. So it is often difficult to know like what is actually possible to achieve. Like if you find yourself maybe having 5% error both on the training and the test set, is this actually, am I in the high bias zone here, or am I already in the low bias, low variance setting here? But definitely something to look at is that you want to have similar accuracy both on your training set and your validation set. Then there is some rules of thumb to apply in case you have either high bias or high variance. So if you have high bias, you would often look at your training data, and here you could make the network bigger, make it have more parameters to train. You can train for longer, or also in regards of bigger network, you can also choose another network architecture. Then if you have a high variance, you would usually look at your validation data, where you would be looking at, could I add some more data to my validation set and also to your training set? Can I do some kind of regularization, or maybe to hinder that you are overfitting, and maybe also a new architecture. And the general thing here is if you have enough data, you would not have any bias variance trade-off. So that's kind of the new thing in the area of big data, that if we add enough data, then essentially we would come into a state where we do not have to do any trade-off. So essentially you can just add more data, make the network deeper, and which will lower the bias, and which will both lower the bias and the variance error in the network. During training, we can add a regularization, which helps to prevent overfitting. And the techniques here below, these are essentially techniques that helps constrain our optimization problem to discourage too complex models. So we want the models to be simpler. It could, for instance, be with weight regularization, which is not often used in deep neural networks, but you might have seen it in other algorithms where we are penalizing large weights. So in this case, we just want one weight close to 0 and penalizing if the weight gets too large. Then we'll be looking at early stopping, dropout, and also data augmentation. Early stopping does exactly like the name suggests, which is stops early, meaning that stop training before we have a chance to do any overfitting to our data. So here is just a dummy example where if we look at the loss, both for the validation and the training error, and here are the number of iterations, then over time, hopefully both your validation and training error would become lower. Then you'll find some optimal point here. And then you can continue training, which might lead into that, in fact, your validation set, the error there would increase. And on the training, it would lower. So from the training side, we are overfitting to our data. So the idea is here that in each step, you would save the parameters of the network. So in the end, you can look at these curves and then you can see, okay, what step should I go back and use those parameters instead of using the final parameters where I have a good a very low error on my training data, but I have a very bad performance on my validation set. An alternative regularization method is dropout. So the idea with dropout is that during training, we would randomly set some activation outputs to be 0. And the rate this would usually be done is 50% chance of the activation function to be active or not. And the main idea behind this is that this would try to avoid that the network relies on single nodes. So in practice, how this would work is that well, for 50%, then we could just do a single coin toss. See, should this neuron here be active? Yes, it should still be active. Should this neuron be active? No, it should not be active. Then we do this for every single neuron in the network, and we end up with a slightly simplified graph where, well, the output for a lot of these neurons is just 0. The downside of this is, though, that the cost function is no longer well defined, so it might not decrease in every step. But if you use batch training, this is anyway the case that we're not computing the gradient over our whole data set, but only a small batch. So in that case, in fact, it's anyway not like it. We might end up in the same scenario that it might increase slightly. Another regularization method is data augmentation. The idea here is that getting more training data can help to regularize, but it can also be expensive to acquire all of this new training data and label it. So for images, for instance, we can add horizontal flipping, random rotation, random cropping. So we have an example here where in the first image we just have horizontal flipping. The last one here we both have horizontal flipping, random rotation, and random cropping. We could also add random distortions, an example here, or some color shifting of the images. But the thing to note is that this is not as good as adding independent examples to the dataset, but it is also much cheaper. So you only have to label an image one time, and then you could augment it, let's say, 10 or 100 times, but only labeling one image, and then you will get 100 data items in your dataset. An important aspect of any machine learning method is data normalization. So why is dataset normalization necessary? Input features of very different sizes will make the optimization take a very long time, as the weight will be in very different ranges as well. So we can just look at an example here where variable x1 has a range from 1 to 1000 and x2 has a range from 0 to 1. So the optimization might look something like this here, assuming that we use some mini batches, let's say. And now let's look at an example where we normalized our inputs to the range 0 to 1, where the normalization would then look much easier. So obviously this here is overly simplified to visualize what normalization does and why it's necessary. In practice, you know, you would have a much higher dimension than just these two, making it very difficult to actually get a visual understanding of how your whole space looks like. So as already mentioned, dataset normalization is an important step in most machine learning methods, so it's not unique just for deep learning. But in general, it's not something you would hear too much about in any other deep learning or machine learning course. So let's just look at an example here where you have two features, x1 and x2. What we could do now is subtract the mean. And then afterward, we can divide this data by the standard deviation, and then we'll end up with our data having some standard normal distribution here. And one very important thing is to remember also to normalize the test data as well, using the same mean and the standard deviation as from your training data. Vanishing and exploding gradients, they are some terms that you might encounter when working with deep learning. So it is essentially terms describing a deep neural network system which has become unstable. So either the gradients has vanished, which means that you will not be able to learn anything more. Like if you have zero gradients, you have nothing to learn from, or your gradients are exploding. So they're so large, your gradients, that your setup will become numerically unstable. So a very easy way to show how this might end up is if we have a network here of L hidden layers. Then for simplicity here, we just have a linear activation function for the neurons. Now it is quite easy to compute the full output. It's just a continuous matrix multiplication of all the weights in our network, as the activation function is just a linear function. And now we can initialize all our weights with 1.5. And what we then see is that if we have this long list of matrix multiplications of 1.5, then we end up that our values becomes goes towards infinity. And this is what is known as exploding gradients. On the opposite side, if we initialize our values to some slightly less than 1, namely 0.1, then we would see by these many multiplications that our values goes towards 0. And this is known as vanishing gradients. And as you might know, the activations GZ are used in backward propagation, which leads to the exploding vanishing gradient problem, and the gradients of the cost with respect to the parameters are just too big or too small. One way to overcome these vanishing or exploding gradients is to have a smart weight initialization plan. And the main idea here is to have some initial parameters which needs to break the symmetry of the network. So two hidden units connected to the same input must have some kind of different initial parameters. Otherwise, they will have the same gradient, they will be updated the same way, and they would learn the same thing. So initializing all neurons with 0 leads to all neurons learning the same features. And what has previously been used is random initialization, weights from a standard normal distribution, 0, 1 here, which can also lead to the vanishing exploding gradients. And one thing also to note is that the bias value depends only on the linear activations of the layer and not on the gradients of the deeper layers, so the bias can in fact be initialized to a constant value. And for most neural networks, you will often initialize the bias to 0. I also include a link here to an online visualization of different initialization methods for deep neural networks, so on deep learning AI. So I also encourage you to go there and have a visual look at how different initialization methods can influence the training of a network. One simple weight initialization method to prevent vanishing or exploding gradients is to follow these two rules, namely that the mean of the activations should be 0 and the variance of activation should be equal across every layer. And one that is often used is what is known as the savior initialization, where all weights for all biases is set to 0, and the weights from a normal distribution with variance depending on the number of neurons in the previous layer is used as initialization. So initializing the weights of a layer, you look at how many neurons did the layer before me have, or before the current layer have. But also people figured out that for ReLU specifically, instead of the savior initialization where you have 1 here on top, then it's better to swap that out with a 2. So at least practical wise, people figured out that works better if you have ReLU activation functions. Alternative methods, which at least I'm not aware that has been used that much, is gradient over threshold, so gradient clipping. So if you see a gradient over a certain size, then you clip it to a certain threshold, or you can also specify a vector norm for the gradient with the derivatives are scaled to. But I think at least that the weight initialization, especially using the savior initialization, that's what much more used in practice. Here I just wanted to add a picture from this paper from Neuron from a few years ago, where the authors they tried to come up with a method that where we could visualize the loss landscape of a neural network. And as you might see here, then it's a very, very hilly landscape, which also suggests that it's very important to do some proper initialization. So instead of, starting over here, you might end even down in a small valley here or so. And if you have a bit smarter initialization, maybe you would initialize your weights somewhere here, such that hopefully you have an easy path towards the global minimum as well. For the optimization of the neural network, we have so far only talked about gradient descent. But in fact, there is a lot of different methods which tries to do slightly better than gradient descent. So essentially, it just looks at how can we find a better learning rate and how can we stabilize the gradient. So all of these methods, what they're trying to do is, they're all variants of gradient descent, and they act either on the learning rate or on the gradient itself, or both, in order to stabilize the training. And usually you would have to try out multiple methods here in order to find what actually works well for you. So now we'll just go over momentum, how that works, which works in the gradient, and RMS prop, which works on the learning rate, and Atom, which is then a combination of these two, which combines both stabilizing the gradient and the learning rate. But before going into updating gradient descent, we'll just have a quick look at what is actually gradient descent. And often, in fact, people mention backprop, and that's what they're using for the optimization. But again, here it's only important to remember that gradient descent is not only backprop. So backpropagation or backprop refers only to the process of backpropagating the error through a computational graph to compute the gradients of the error function with respect to the weights of the graph. And gradient descent is then after you have all your partial derivatives, then use this iterative approach to find a minimum of a function. And the algorithm then takes a step proportional to the negative of the size of the gradient. And then we have the loop here where we compute the gradients of the loss function with respect to all the weights in the networks, all our partial derivatives. And then our new weight is our old weight minus some lambda, it's the learning rate, and the gradient of the weight. We iterate this, and after we converge, then we return the final weight of the network. In more modern systems, we have so much data that in fact we cannot have all the data in memory and compute the gradient upon a full data set. So what is often used is mini-batch gradient descent. So we can look at an extreme version first, which is stochastic gradient descent, which performs an update for each training example in the dataset. And an extension of that is then mini-batch gradient descent, which is a mixture where the cost is computed from random subsets of the training data. And this is what is called mini-batches of our dataset. So here we have just a formulation for mini-batches, mini-batch gradient descent, where we have m training data at a time that we compute our gradients from and take a step in that direction. So having these mini-batches, it's way more efficient in terms of memory consumption and computational cost instead of having to compute your gradient on your full dataset. Though there is some problems, which is especially fluctuation in the cost function, which might increase in some mini-batches. And then some deep learning terminology, which is one epoch is the entire dataset passed through the network one time. So you might have a dataset of 1,000 images, for instance. You have a mini-batch of 100, so you have to take 10 mini-batches to have one epoch. So to be through your dataset one time. If we just look at gradient descent and how it's optimizing, then it takes a small step towards the negative of the gradient. And this step is proportional to this to the learning rate that we're setting. So if we're setting too small learning rate, then it converges slowly and gets stuck in false local minima. If it's too large, then we might overshoot and become unstable and diverges. And then obviously what we want is some stable learning rate, where it converges smoothly and avoids local minima. And also here, for the learning rate, I advise you to go to the Deep Learning AI website here, under their AI nodes and optimization, and have a look at different optimization techniques, and also trying to set the learning rate for these small examples. One way to help control this learning rate of the gradient descent algorithm is using what is known as learning rate annealing. So using standard gradient descent, what we'll do is select one learning rate, and if it's too small, we will end up in here on the left that we have to take a lot of small steps in order for us to get to the minima. If it's too large, we have a whole other problem that we are getting further and further away from our local minima. And if we're smart, maybe using some kind of learning rate annealing, then we have a decent size in the beginning, which then gets smaller and smaller the closer we get to our local minima. So using basic gradient descent, standard gradient descent, the value of the cost function, it can oscillate back and forth when getting closer to the minima. So the idea is to slow down the parameter update by decreasing the learning rate the closer we come to our target. This can be done manually, but there is also quite some automatic methods which tries to do this. So one way to control the learning rate is using this learning rate annealing method, Adagrad. And what it is doing is it adapts the learning rate by dividing with the cumulative sum of current and past squared gradients for each feature independently. So we see here that we have our learning rate, but then it's divided by the squared gradient of the weight, and we also have plus some small epsilon here just to be sure that we're not dividing by 0. This here is beneficial for training, since the scale of the gradient in each layer is often different by several orders of magnitude. But a problem here is that the learning rate will eventually become close to 0 due to the accumulated sum in the denominator. So a method that tries to get rid of this, the learning rate eventually going to 0, is the RMS prop, root mean squared prop, which, as mentioned, solves the diminishing learning rate in Adagrad. And the idea here is to adopt the learning rate by dividing with the root of squared gradients. So, and beside that, then uses the moving average to smooth over multiple mini batches. Instead of just having one batch that it uses for smoothing the learning rate, then it uses multiple. And with RMS prop, then higher learning rate is possible as we smoothen out the gradient, smoothens in the gradient direction. So here is just one visualization, very rough visualization of how mini-batch gradient descent might fluctuate during optimization, and how RMS prop is then slowing the learning rate perpendicular to the direction of the local minima, and makes it faster in the direction of the local minima. And some standard values here to choose is beta 0.9999. And what this means is that we are relying heavily on pass on pass values of the squared gradients, and only adopting our learning rate here as t slightly. So it's only 0.001 of the current gradient, of the current squared of gradient, that we actually using to adjust the learning rate. A funny thing here to note is that there is another method called AdaDelta, which was developed at the same time, completely independently, But at a delta, there is actually a paper describing that, whereas RMS prop that was introduced during an online course on deep learning. Instead of doing smoothing on the learning rate, we can instead do gradient smoothing. And this is exactly what momentum is doing. So momentum tries to smoothen out the fluctuation in gradient direction from using mini batches. So how is it doing this? It is adding a fraction of the update vector of the past time step to the current update vector. So momentum increases for dimension whose gradient points in the same direction, and momentum decreases in dimension whose gradient change directions. And the idea here is that we would have faster convergence and reduce oscillation in our system. So the formulation here for momentum, as we see, instead of just having the gradient here, we would instead have mt, which then takes gamma from the previous time steps and only adds a fraction from the current time step to our gradient computation. And on the picture here to the right, which looks a lot like what you saw also in RMS prop. So in practice, they do a lot of the same things, but one, you should just remember, works on the learning rate and the other one works on the gradient smoothing. So they both try to do the same thing, namely smoothing out the oscillations in training, which usually occurs from using mini batches. And the default value for momentum here is 0.9, so you would also mainly use gradient like the historic gradient, and only update your gradient from the current mini batch slightly, so like only 10% from the current mini batch. Then we have Atom, which now tries to both work on the gradient and the learning rate. So it's essentially just putting together momentum and RMS prop, and it also adds some bias correction for the first and the second momentum. So here we have momentum and RMS prop, and the bias correction, which you might have seen that there could be a problem. So especially for RMS prop, which uses a beta as 0.999 for all the previous values, which means that the system will take a long time to actually warm up. So in the beginning, we would have this part here, and also this part here would be 0. But using this bias correction, we can have some kind of decent value in the beginning instead of just wait for the system to warm up. So if the bias correction is not used, the momentum and RMS prop terms are biased towards 0, especially during the initial time steps or using small decay rates. So it is very important for you not to have a system that essentially doesn't move to begin with, to use this bias correction as well. And the hyperparameters, or the values here for gamma, beta, epsilon, they are the same as for the individual momentum and RMS prop. Then I would again advise you to go to deeplearning.ai on their AI nodes and optimization and have a look at the difference between all of these algorithms, so momentum, Adagrad, stochastic gradient descent, RMS prop, Atom, how they are, how the training looks like for different data sets, and using different hyperparameters in these optimization algorithms. So here on the slide is just one example of the training, and what you see is both the training and the testing data, so the orange and the blue here. So before we end the slideshow here, there's just one more method to talk about, which is batch normalization. So we already talked about dataset normalization, which is normalizing our dataset. So for the first hidden layer, essentially, we'll be normalizing our data. But batch normalization, what that does is trying to normalize the activations in a network. So normalizing before or after the activation is possible, but this is mainly done before. So as such, there is nothing hindering you from doing it after. Just in practice, what people are most often doing is right before the activation function. And I'm also not sure if it have that much a difference if you do it before or after. So the idea is to normalize the activation outputs for faster training. So also to have all the values before the activation function to be in a nice standard normal range. And this is to be sure that the activation function input is in a good range. So for instance, especially if you use something else than like sigmoid activation functions, then it's really important that you are close to 0 to be to have some gradients that actually are meaningful. So let's look at an example of batch normalization from a single neuron's point of view, and also some of the problems or you might see using this batch normalization. So essentially, normalizing the mean and the standard deviation of a unit can reduce the expressive power of the neural network. So in order to maintain this expressive power, we also introduced 2 new learnable parameters. And how does this then look like graphically? Well, we have our maybe just all our inputs from the previous hidden layer, from all the neurons there, to the variable C, also all the bias terms or the bias terms here. Now we're normalizing this C value here, subtracting the mean, dividing by the standard deviation, and then afterward we add these 2 new learnable parameters, gamma and beta. And one thing to note here is that these gamma and beta have nothing to do with the gamma and beta used in Adagrad, RMS prop, or momentum, or atom for that sake. They are, by coincidence, just with the same variables or the same names here, gamma, beta. But as such, they have nothing to do with each other. And then finally, we can compute the output activation based on these, the normalized, and after the normalization, we multiply by gamma plus beta. And then we run this value here through the activation function. So the mean here and the standard deviation or the variance here, they're computed based on the C values in a hidden layer for each mini batch. And some way to look at it is now that in the parameterization, we computed the mean variance determined by interaction between parameters in the layers below. And then there is some kind of new parameterization where the mean and the variance is determined solely by these 2 hyperparameters, gamma and beta. So these are 2 learnable hyperparameters. So one thing, at least I find a bit counterintuitive here, is that we have C, we subtract the mean, and we divide it by the standard deviation here in normalization. But then afterward, we take this normalization, then we add something which could essentially be equal to the standard deviation, and then we plus beta, which could be equal to the mean. So if we set mu equal to beta and the standard deviation equal to gamma, then we would be back to the state where C here goes directly in the activation function, and then we have just done a lot of computation here for no need. But people at least have shown that this here, learning these mean and variance values here, that is a much better way to do the normalization between the layers in a network. So just as a note here, in also for practical implementation for the test time, we should then use a weighted average across all the mini batches for the mean and the variance values here. So this one and this one here. Finally, as a summary of all this hyperparameter talk, then hyperparameters, they should be tuned on a validation set, not on the final test set. And for regularization, what you would mainly use is early stopping, dropout, or dataset augmentation. And you have to choose an optimization algorithm that suits your needs, or you could also use a general good optimizer like Atom. So I'll definitely say that Atom is the most commonly used nowadays optimizer for deep neural networks. And one place to start tuning your network is by looking at the learning rate. So we went over like a lot of different hyperparameters that you could start tuning, but really start out with the learning rate to see if when you set that too low or too high. And another thing is you should also try out, when you're training a deep neural network, try out with different batch sizes. So going all the way from 1 to essentially the dataset size, if that's possible to keep all of that in memory. So quite often you find something in between where it's fast to train. It doesn't take too long time for each epoch, and yeah, it can still stay in memory. And on the last slide here, just again some links to all the different materials that was used for the creation of these slides.